Hello, welcome to the fourth in this series of Digital Twin Talks looking at interconnected digital twins. I'm Tom Hughes, the delivery lead of the Digital Twin Hub and facilitator for this Twin Talk series. Today, I'm introducing David McKee, the CEO and founder of Slingshot Simulations. David's a Royal Academy of Engineering Enterprise Fellow and has been working on co-simulation, which is digital twins integration and interoperability, since 2013. Just one piece of housekeeping before I hand over to David. As with all the Twin Talks, David, myself, and other members of the CDBB team will be online for a live discussion at 10:30 a.m. on Tuesday. Please bring your thoughts, questions, and challenges to the DT Hub for myself, David, and the team. Thank you. Over to you, David.
So for the next 10 to 12 minutes, I'm going to look at why digital twins really can happen now and why over the last 20 years it has actually been quite hard to achieve it using the technologies that we had available. I'm going to look at a few challenges that we've been facing as an industry over the last couple of decades and what have been the key enablers that allow us at Slingshot and other companies to embrace digital twins now today in 2020. So to start, I'm going to kick off. We can't have any digital twin discussion without, first of all, looking at a definition of that, then going to look at some of the key challenges that we face as an industry and how some of those have been overcome over the last few years. Then going to move towards the Slingshot approach, looking at what are those enablers that have overcome some of those challenges with what we at Slingshot call the 3 Cs. And I'll finish off with our approach, looking at some of the key technology stacks and frameworks, APIs, and so forth that we use to achieve co-simulation or digital twin integration. But first, let me start with a very brief intro to Slingshot. So we are a spin-out from the University of Leeds. We formed in summer of 2019, building on over a decade of research in large-scale simulations with some of the world's largest engineering firms, people like Google, iCloud, Jaguar Land Rover, and Rolls-Royce. In 2016, we rolled out the world's first digital twin of a data center that combined both the software architecture as a model and the thermodynamic behaviors of a data center, allowing us to help iCloud reduce their energy footprint by over 50%. The Slingshot team is primarily comprised of cloud engineers, which makes us a really unique team in terms of the simulation and digital twin world. And since 2016, we have been working towards defining a standard of an internet of simulation or an internet of digital twins or virtual things using our simulation as a service paradigm. So that's enough about kind of Slingshot. Let's dive into what is a digital twin. Hopefully everyone will recognize this. This is CDBB's definition that you can find on their website and so forth. I put this here because at Slingshot we use a very subtly different definition, but one that we feel is quite important given the domains that we work in. We refer to a digital twin as being a digital environment, specifically referring to the fact that we work a lot in terms of geospatial, deal with things like air quality, and utilities, ground movements, and so forth. So trying to encapsulate more of that natural environment in our definition. It is a digital environment that reflects on, mirrors, and evolves ahead of the physical environment or service. Now, there's a caveat here that needs to be added to digital twins that we could be describing processes as well that people do or that are done by physical systems. And then a key aspect is that this is in order to facilitate smart decision making. And I'll mention the smart decision making in a moment. And then for us at Slingshot is then all about storytelling for stakeholders. So not just the people who are probably in this meeting, but about saying actually how can we get everyone to understand it, whether it's the person on the street, whether it's a councillor, a politician, or a venture capitalist. Whoever it is needs to be able to understand what is the story being told. And digital twins provide a really powerful tool for this. Starting with that, so at Slingshot, our vision is about making digital twins available for anyone. Back in 2016-17, digital twins really were limited to the billion-dollar companies. Even Gartner's report, which predicted a huge adoption of digital twins by this year, was only targeting those companies who are $1 billion plus. So how can we actually make digital twins usable and accessible to SMEs, to even the $500 million companies? And actually that's through a couple of key aspects. One, it's about making it timely, being able to do rapid prototyping and building digital twins, using them quickly and effectively in a timely manner. Let's give a quick example of that. If we take the current COVID situation, if we were to do a digital twin of a building or city centre looking at how can we return to work, taking 9 months to do that analysis isn't acceptable, because by that point, we'll have hopefully already returned to work. So actually the turnaround time then needs to be really quick, needs to be short in a matter of days or weeks. And one of the most important things that we too often see is there has to be a meaning and a reason behind doing this. And that ties back into that speed. It's about doing it in a timely manner, but actually really think about why are we doing it? What level of detail do we need in order to answer the questions we need? What data sources do we need? And what are we measuring and why? And most importantly, in order to actually make it usable for anyone and to truly democratize digital twins, we have to make it accessible and understandable and usable by anyone. We've got clients in every industry, people who quit school at 16 and who are scared of Excel, to PhD biologists who I have no idea what they're talking about. So there really is every spectrum, and we need everyone to be able to use them and actually retrieve the benefit of it. So that being said, what are some of the key challenges that we see and we've seen over the last decade? And they fall into 4 categories. We've got social, technical, time-based, and cost challenges. From a social perspective, this is all about understanding ownership and then liability. Let's take an example from the automotive industry here. So you might have someone like Bosch who builds electrical control units for transmission systems and so forth. They are not going to want to share the inner workings of those models with the automotive supply chain, because that is their IP. They're really keen to keep that. And we can see that across many other areas of business, whether it's the logistics industry, who don't want to share the nuances of their operation because 1% efficiency saving would give their competitors an advantage. They also don't want to share something which might become a liability. And this we see too often, even within an organization, where a junior engineer might not want to share the inner workings of a model because it says, well, actually, I've kind of hacked this together. It does it, but I don't want my boss to see it. And that requires a social change in terms of how we interact. And particularly in the UK, we are quite private. So this is quite a challenge. Beyond that, we then get into a corporate level where we actually are trying to encourage companies to be more open with their data and to share that more whilst trying to find the right balance of confidentiality and privacy, whether it's GDPR or commercial. Moving away from the social side to what we personally find more interesting is some of the technical integration challenges. So this could be scale. To give you an example, we've currently got a project underway where we're generating roughly 10 gigabytes of data per second. That's a lot of data, and actually understanding that, storing it, processing it is a challenge. Then doing something interesting with that. Now, I'm going to stick with the automotive example because I think it works quite well here. If you're to take a digital twin of an engine and a digital twin of a transmission system, there are over 500 interdependencies between those two in a typical model. And they need to be correctly wired together, and it can be a spaghetti mess. So understanding that, putting that together and having an engineer who's skilled to do that and can do it quickly is really, really challenging. But then in complexity, we also have challenges of time integration, challenges of the fact that different people use different naming conventions. Great example are some of the things we've seen with NASA over the last few decades, where they've used imperial units and we use metric. How do you make those different assumptions? How do you integrate those together? Documentation is one way, but that's not always the only way. But then underpinning all of that is also security. One of the biggest challenges there is we can't encrypt all the data because that slows everything down. It could slow things down by sometimes a magnitude of 10,000 times if you use the most advanced forms. So how do you make this secure? Maybe encryption whilst at rest, at the very least using HTTPS and other mechanisms such as two-factor authentication. And then going a step further, a bit more of a deeper dive here on a technical challenge. This was something that we've seen across several industries, is when you take digital twins from different domains or different engineers, and you want to put them together, there's a concept of time. So let me give an example which is not engineering based, and I would typically do this by getting two people in the audience to stand up and walk across the room. But hopefully you can use your imaginations and follow with me. Imagine you have two people who are at opposite ends of the corridor. They're blindfolded and they have to walk down the corridor, meet in the middle and shake hands. But they're blindfolded and they're not allowed to talk to each other. The reality of what actually happens is a very awkward encounter where you hope they know each other quite well because they bump into each other. And I've seen plenty of examples where this can be quite amusing for the rest of the audience. But when you're integrating two black boxes, which are digital twins, which are software, and that can't figure that fumbling bit out of actually, right, okay, how do I shake hands? Where's your hand? Software is much harder. How do you integrate that? There's two primary approaches we see in the engineering industry that are known as a zero order hold and a first order hold, which is where you look at the data outputs that are coming out and you predict it based either on the current value or on the gradient of the data that's coming. So you're predicting what the next value will be. And here on the screen, the little red line on that graph is showing a potential prediction. But let me give an example where this is clearly wrong. Imagine that line is representing the speed of a car. And you're accelerating the car and you're not predicting that it's going to continue accelerating because the computer doesn't know any better. But when you get the data a few seconds later, actually you found that you took your foot off the accelerator pedal, so you didn't continue accelerating. Now what that means is when you update your model with new data, you actually get an infinite gradient, i.e. the vertical line that is dropping there. And I don't need to tell anyone that it is not possible to have an infinite and immediate change in speed. It's a physics impossibility. So how do you deal with that? And the current techniques really don't tackle it. And this is a real challenge in a lot of the industry. And then the other side of that is imagine you're modeling everything from finite element analysis to fluid dynamics. The compute you need to do this is huge. And if you're an SME, such as ourselves, we can't afford several £1,000,000 of buying an HPC. So we need to use other techniques such as cloud computing to actually achieve the real-time analysis that might be required. And underpinning all of that, of course, is cost. From setup cost to the staff cost. Engineers who understand how to do all of these different parts are expensive. And again, SMEs typically can't afford them. And even we sometimes struggle to recruit staff because we can't afford some of the people we need. Now, a lot of these are no longer issues. A lot of these have really been stripped away as problems if we actually look at the computing industry, specifically if we look at cloud computing. And as cloud computing specialists, we see the world operating in terms of these 3 C's, in terms of collaboration, computation, and communication. We've all got mobile devices. We've got Internet of Things sensors everywhere. I've got a Google Home device in 3 rooms at home. We're so connected, and we need to be able to use that and take that and adopt it in our industries in terms of how we deal with simulation. We've got almost infinite compute available with Google Cloud, AWS, or Azure. Using all of that puts us in a really unique position where we're actually able to do simulation integration in a way that we've not been able to do before. So at Slingshot, how do we do this? And we split it into 5 phases. You have an imagination phase where you do not limit yourself by what you think is possible. You don't limit yourself by what you've seen before. You say, well, what is it that I need to do? What is the story I need to tell? And that links back to that play aspect of imagine this is a computer game. Don't limit yourself. Think about sci-fi. Think about all those different possibilities of what's possible. You then feed it data, feed it more data, probably feed it more data again, and then do something intelligent with it. In terms of feeding it data, what we're talking about here are some key challenges that we need to address. We need to understand the data formats in terms of everything from file types. If it's 3D models, are we talking about OBJ files, GLTFs, FBXs, etc.? Are we talking about CSV files, but what different naming conventions for columns? Could be XML sources, all these different types of things. How do we unify a certain amount of that? But also, can we use machine learning with natural language processing to recognize that if someone has tagged something as a car, but in another one is tagged as a vehicle, they're kind of the same thing. And using ontologies and a level of machine learning to map those things together. But also using aspects such as symbolic regression to profile data. So you don't necessarily need to store it all, but you're understanding the shape of it. Now at Slingshot, we deliberately use symbolic regression over traditional deep learning techniques because we believe in having the models fully transparent from an audit and liability perspective, so that someone who was understanding of the art would be able to explain why it does something. So let's dive a bit more into that data aspect. Our fundamental data structure at Slingshot is a unifying data structure that we base on a geospatial reference point. So using UTM coordinate space, which is converted from longitudes and latitudes. On top of this data, we load in other data sets with references to those. Here is actually a visual representation of a data structure we've got with Leeds City Council, where we've got an ongoing digital twin project. For every point on this image, for every blue dot, every line, there is a data set associated with it of a particular format. Because it's in that format, we're able to relate that to stakeholders in the council. We're able to say, for this building, for this street, for this platform on the train station, these are the data sets that are associated with that area, rather than having to go through a data warehouse and try and find one based on some naming convention that they may not be aware of. And that has been probably one of the biggest wins for us in terms of particularly the last 6 months, as we think about how we present and relate data together. But that also means you can add other data and you can start to interact with it. You can layer on ANPR data for vehicle counts. You can have pedestrian data. You can start interacting with it and creating a very dynamic model, looking at what's possible. But that in itself doesn't necessarily get you anywhere. What you need to feed into that is a lot of data. So these models that we're seeing here include a lot of open data. So we've got OpenStreetMap data, NASA satellite data in terms of topography. We've got European Space Agency data in terms of air quality as well, and then footfall sensors from various APIs. All of that needs to be fed in and standardized to a certain format. And we are very, very picky about what data sources we work with, as I'll allude to in a second. Underpinning this approach is a systems-to-systems approach. As a computer scientist, this is our natural bread and butter. And this diagram from CDBB really highlights this quite nicely for the rail sector, where we look at how we take individual assets, individual digital twins or simulations. They need to be linked together as assets within a systems or systems model. And slowly you build up a hierarchy of models or digital twins of digital twins that are interrelated, can operate together, can work together and provide added value where the sum of the parts is much greater than the individual parts. In order to achieve that, however, we need standards. At Slingshot, we are very, very picky about what standards we use. So we are, with all our simulations, every simulation runs as a service in the cloud. Now, it can be our own bespoke solution, or it could be a third-party one running in a virtual machine, but it must be compliant with one of these two standards. So we insist on using either the RESTful OpenAPI 3.0 standard or using the IEEE high-level architecture standard, which is currently going through its 3rd iteration. The OpenAPI is a standard web standard, whereas the HLA standard is a NATO standard for co-simulation. Between these two, they cover 90% of what we need. We also address that aspect of time integration that I alluded to a few slides ago, using a particular approach where we actually use machine learning to understand the derivatives. And I won't dive into the mathematics of it, but I'll be happy to discuss it further with anybody who's interested. And we start forecasting different possibilities. So we run multiple copies of different simulations to understand and then prune that. And actually, it's almost like a Google Maps saying, actually, you've got 3 different routes available to you. We think this one will take 5 minutes longer, this one's 5 minutes shorter. And then you prune them actively to see what's possible. Costs more to run, but you get more accurate results as a result. And then underpinning all of that has to be a compliant communication backbone. So we use the ISO 19464 AMQP standard, which is a pub sub, so publication subscription standard, again, which has derived from the defense sector, where you can have multiple simulations running and interacting, listening in and communicating across a backbone. And then before I finish on that, the most important thing is making it secure. So we at Slingshot use the SOC 2 standards or ISA 3000, and I would highly recommend people look into those. As I come to finish, I want to move away from that technical aspect and think about something really, really simple, in the sense that in order for digital twins to be adopted, and in order for integration of these to actually work, it needs to be as simple as painting by numbers, which is an incredible challenge when I start talking about differential equations, which is definitely not as easy as painting by numbers. But it needs to be that easy. It needs to be like connecting the dots in terms of literally drawing and saying these data sets are related to each other. And then saying, actually, this is the data sets we need for this question, and having that as a resource and be able to pull it together. And underpinning that has to be a level of standardization, as well as all the things I've alluded to. I'd like to finish there. Hopefully that's been a very interesting few points that spark people's imagination of what is possible, but also raises some questions around technology frameworks that we feel really have been paving the way for the last probably a decade or so in terms of co-simulation and integration of digital twins. Thank you.